Okay, so we're continuing on with page 17. Finding the interval of convergence. For what values of x does the series converge absolutely, and for what values of x does the series converge conditionally? So we're going to go ahead and run the ratio test, and then we have to test the endpoints. Okay, so we're going to go ahead, the limit as n goes to infinity, the square root of n plus 1, the absolute value, oh no, actually this is supposed to say, replace this with x to the n. That is written incorrectly. X to the n plus 1 all over 3 to the n plus 1, and that's divided by the original, square root of n, x to the n, 3 to the n. Flip the guy. Square root of n plus 1, 3 to the n plus 1, x to the n plus 1, times 3 to the n all over the square root of n, x to the n. Now that you've done so many of these, you probably can already tell what's going to happen, and that's a good thing. So looking at 3 to the n, 3 to the n plus 1, x to the n plus 1, and x to the n, using our rules of exponents, that gives me x in the numerator, 3 in the denominator. I get the square root of n plus 1 in the top, the square root of n in the bottom. So anything not involving n, we move outside. So this gives me the absolute value of x over 3, and the limit as n goes to infinity of under 1 square root n plus 1 over n. And actually I'm going to rewrite this. This divides each term, and this limit will be super clear. So this becomes a square root of this over this is 1 plus 1 over n. So if I take the limit, this goes to 0, this whole limit goes to 1. So like before, we're taking the absolute value of x over 3 times 1. To guarantee convergence, this has to be less than 1. So essentially what we're doing, and I'm going to draw a little arrow to save room, we have to solve this inequality, and removing the absolute value signs gives us this. And then to get x by itself, multiplying through by 3, you get minus 3 is less than x is less than 3. So this is our, or this kind of is, this is our interval of convergence until we talk about the endpoints. But for right now, this is what we have. We need to investigate these two endpoints. Remember, when you run the ratio test, that the ratio test is a test for absolute convergence. So now we're going to, I'm going to draw a line, and we're going to test endpoints. Let's do the easy one first, x equals positive 3. So we go back to our original equation, and anywhere there's an x, we put in that value of x. So our original series would become the square root of n, 3 to the n, all over 3 to the n. So just like before, nice things happen. And we're simply looking at this series, n equals 1 to infinity, and we're left with the square root of n. So if we just consider the nth term test, this goes to infinity, so it's something other than 0, and we know that we diverge by nth term. So this endpoint is not included. Okay, let me go turn the light on. Now we have to test the other endpoint, so this time we're going to test the endpoint x equals negative 3. And like before, we're just plugging that in. So we get the square root of n, and this time it's negative 3 to the n all over 3 to the n. And in simplifying, what we've created for ourselves is an alternating series. So let's pull out the term that's affecting the negative. So this is minus 1 to the n, 3 to the n, all over 3 to the n. The 3 to the n's cancel. And so now we're looking at n equals 1 to infinity, the square root of n times negative 1 to the n. So since this is alternating, we're going to use Leibniz's theorem. So we need to do 1, 2, 3. So following the process that we've developed, our use of n is the square root of n. So our three criteria are use of n's are always positive. Check. And what about use of n plus 1 is less than or equal to use of n? Well, if we think about what happens as n grows, the n plus 1 term is actually going to be bigger. So this is a fail. So we fail Leibniz's theorem. So we diverge. So we actually end up diverging at both endpoints. So we don't even need to run the third test once we fail. So in summary, for our problem, our interval of convergence is actually what we ended up with from the ratio test, -3 less than or x, less than x less than 3. We converge absolutely on the same interval, and we converge conditionally nowhere. Okay, we're going to move on to the next problem. Here will be an example of where we actually have a situation where we're going to we will have some things that are conditionally convergent this time. Okay, so given this equation, the series, where do we converge absolutely and converge conditionally and find the IOC? So again, the ratio test to get the IOC and test the endpoints. Okay, so higher levels of complication this time. Just our series is a little bit more, oops, a to the n, no, that was right. Excuse my mess. A little bit more complicated. So everywhere we replace n with n plus 1. So n plus 1, x to the n plus 1 over 4 to the n plus 1. And then we have to be careful here. N plus 1 squared plus 1 divided by n x to the n all over 4 to the n squared plus 1. Okay. So I'm going to say n plus 1, x to the n plus 1, 4 to the n plus 1. And let's start, oops, I guess I only needed 1. Let's pretend I didn't do that one. Let's make it all solid. Okay, let's FOIL this out. So this becomes n squared plus 2n plus 1 plus 1. So we can simplify that to be n squared plus 2n plus 2. We're going to flip the guy, so we have 4n, n squared plus 1, divided by n x to the n. So we have a lot of simplifying we can do here with our rules of exponents and here. So I'm left with an x in the top, a 4 in the bottom. And then I have n plus 1, n squared plus 1. And I have n times n squared plus 2n plus 2. So I'm going to move the x over 4 out front. And I'm going to FOIL this thing out. So we get n cubed plus n squared plus n plus 1 all over n cubed plus 2n squared plus 2n. So I could L'Hopital 3 times, or if I can remember the rule from chapter 2 where if you take the highest power of the numerator and the denominator and they have the same power, you could just take the